next shape we will look at is a charged plane. For this shape we will also use a Gaussian surface, which is a cylinder, and we're going to put it going through the plane. So starting with the left-hand side of Gauss's law, when we integrate over the surface of the cylinder in this case, we only need to include the ends of the cylinder. The electric field from a plane points straight out at normal to a plane, so there will be no flux lines going through the main curved side of the cylinder in this case, only through the ends. So the total surface area is 2 pi r squared. There is 2 because we need to include both ends of the cylinder, as field lines come out of both ends. Moving on to the right hand side of Gauss's law, we just need the total charge enclosed by the cylinder, which is the charge per unit area times the area enclosed. The area on the plane which is enclosed by the cylinder is just 1 pi r squared, not 2. Equating the left and the right hand sides of Gauss's law and rearranging gives us this expression for the electric field due to a charged plane. Notice that the pi r squared for the area on the ends of the cylinder on the left hand side and the pi r squared for the area of the plane enclosed by the surface on the right hand side, they cancel out. So it didn't matter what shape we used. So if, for example, we had used a rectangular Gaussian surface going through the plane with a square on each end, so the squares have an area of r squared, the r squareds would still have cancelled out and we would get the same result. Another thing to note is that the final equation does not depend on r. So if you're right next to the plane, or you are on the other side of the universe, the field is exactly the same. For this to work, though, the plane does have to be infinitely large, or as you move further away, it would start to approximate a point charge, for which the electric field decreases with 1 over r squared.